Imagine you are watching an electron, just sitting there, observing it, trying to see where it is. And the very act of looking at it, the simple act of measurement, fundamentally changes what the electron is doing. Not because you bumped into it accidentally, not because your equipment is clumsy, but because that is how reality actually works at the quantum level. The universe doesn't let you watch without participating. Measurement isn't passive observation. It is an interaction that transforms the system you are measuring. And this isn't philosophy. This isn't interpretation. This is what the mathematics of quantum mechanics absolutely demands. See, before you measure an electron's position, it doesn't have a position. Not in the sense that it is hidden and you just don't know it. It genuinely doesn't have one. The electron exists in what we call a superposition, a mixture of many different possible positions all at once. It is not here or there. It is here and there, simultaneously, in a very real physical sense. And the moment you measure it, the moment you actually look to see where it is, something incredible happens. That superposition collapses. All those possibilities vanish, except one. The electron suddenly has a definite position. Your measurement didn't reveal where it was. Your measurement created where it is now. I know what you are thinking. This sounds crazy. This sounds like someone made a mistake in the theory. Like we're missing something. Like there must be hidden variables we haven't discovered yet. That would explain what is really going on. And I understand that reaction completely. Einstein felt exactly the same way. He spent decades arguing that quantum mechanics must be incomplete, that there had to be some deeper reality underneath all this probability and uncertainty. But here's the thing. Every experiment we've ever done, every test we've devised, every clever attempt to catch the universe cheating has confirmed that quantum mechanics is right. The electron really doesn't have a definite position until you measure it. Reality really is that strange. Let me give you a concrete example, the double-slit experiment. You've probably heard of it, but let me walk you through what actually happens, because it is genuinely mind-bending. You take a source that shoots out electrons, one at a time, just individual particles, and you put up a barrier with two slits in it. Behind that barrier, you have a detection screen that lights up wherever an electron hits. Simple setup. What happens? Well, if you are thinking of electrons as little particles, like tiny bullets, you'd expect them to go through one slit or the other, and make two bright bands on the screen. One band behind each slit. That is what bullets would do. That is what common sense says should happen. But that is not what you see. Not even close. Instead, you see an interference pattern. Multiple bands of light and dark spread across the screen. The exact pattern you'd get if you sent waves through those slits. Waves that spread out, overlap, and interfere with each other. Places where the waves add up, you get bright bands. Places where they cancel out, you get dark bands. But wait, we're sending electrons through one at a time. Individual particles. Each electron goes through and hits the screen somewhere. There is nothing for it to interfere with. It is traveling alone. And yet, as you build up the pattern electron by electron, dot by dot, you see the interference pattern emerge. Each electron somehow knows about both slits. Each electron is interfering with itself. It is acting like a wave that goes through both slits simultaneously, even though it is a single particle. That is the superposition. The electron is in a mixture of going through the left slit and going through the right slit. Both paths at once. No, here is where it gets really weird. Here is where measurement comes in. Suppose you decide to watch the slits. You want to know which slit each electron actually goes through. So you set up detectors at the slits. Gentle detectors that can tell you which path the electron took without destroying it, and you run the experiment again. What happens? The interference pattern disappears, completely vanishes. Now you see exactly what you'd expect from particles. Two bright bands, one behind each slit. No interference, no wave-like behavior, just particles going through one slit or the other. Exactly like bullets. Your measurement at the slits has changed the outcome of the experiment. Not because you disturbed the electrons, not because your detector was too rough, but because the act of measuring which slit the electron went through forced it to actually go through one slit or the other. You collapsed the superposition. You made the electron choose a definite path. And once it has a definite path, it can't interfere with itself anymore. The wave behavior disappears. Take away the detectors. Don't measure which slit. The interference pattern comes back. Every single time, measure which slit. The interference vanishes. Every single time, the electron knows whether you are watching. Not because it is conscious, not because there is anything mystical happening, but because measurement is a physical interaction that fundamentally changes the quantum state of the system. You know, when I first really understood this, it bothered me for months. It still bothers me sometimes. The idea that reality at its most fundamental level isn't definite until you measure it. That particles don't have properties sitting there waiting to be discovered. That the act of observation participates in creating the reality you are observing. It goes against every instinct we have about how the world works. But that is the thing about quantum mechanics. It doesn't care about our instincts. It doesn't care about what seems reasonable or intuitive. It describes reality as it actually is, not as we wish it would be. And reality, it turns out, is far stranger than we ever imagined. Let me tell you about the uncertainty principle. Not the vague popular version. The real thing, what it actually says. The uncertainty principle states that there are pairs of properties like position and momentum that you cannot measure simultaneously with perfect precision. The more accurately you know one, the less accurately you can know the other. And this isn't a limitation of your measuring equipment. This isn't because we haven't built good enough instruments yet. This is fundamental, written into the structure of quantum mechanics itself. Here is why. To measure an electron's position precisely, you need to interact with it using something with a short wavelength. Light, for instance. Short wavelength light can pinpoint a position very accurately. But short wavelength means high energy. And when you hit an electron with high energy light, you give it a big kick. You change its momentum significantly. So yes, you know exactly where it was at the moment of measurement. But now you've completely disturbed how fast it was moving. You've traded knowledge of position for uncertainty and momentum. Conversely, if you want to measure momentum accurately, you use long wavelength, low energy light, gentle interaction. Doesn't disturb the momentum much. But long wavelength can't localize position very well. The measurement is fuzzy. You know the momentum precisely, but you've lost information about position. There is no way around this trade-off. It is not about being careful or clever with your measurements. It is about the fundamental nature of quantum states, and here's what makes it truly strange. Even before you measure anything, the electron doesn't have both a definite position and a definite momentum. It can't. The universe forbids it. This is different from just not knowing. If I put a coin in a box and close it, the coin is definitely heads or tails. I just don't know which until I open the box. But the electron isn't in a definite state that I simply haven't observed yet. The electron exists in a superposition of different positions and different momenta. Both uncertain, both spread out, both genuinely indefinite until measurement forces a choice. Think about what this means, the properties we consider most basic, most fundamental to what something is position and velocity. These don't exist as definite values in the quantum world. They're not there waiting to be discovered. They emerge through measurement. Reality at the quantum level is probabilistic, uncertain, and interactive. Measurement doesn't reveal pre-existing properties. Measurement participates in creating those properties. Now, there is something even stranger I need to tell you about. Something called entanglement. Einstein called it spooky action at a distance, and he hated it. Absolutely hated it, but it is real. And it shows just how deeply measurement affects reality in quantum mechanics. Here is how it works. You can create two particles in such a way that their quantum states are linked, entangled. For example, two electrons whose spins are correlated. Spin is a quantum property. You can measure it along any axis, and you'll find it is either up or down along that axis. Now, for an entangled pair, the rules of quantum mechanics tell you that if you measure one electron and find spin up, the other electron will definitely be spin down. Perfect anti-correlation. But here is the key before measurement. Neither electron has a definite spin. They're both in superpositions, both uncertain, and yet they're correlated. The state of the pair is definite, even though the state of each individual particle is not. This is what entanglement means. The particles don't have individual quantum states anymore. They share a joint state. Now separate these electrons. Send one to a lab in New York and one to a lab in California. Miles apart, they're still entangled. The quantum state linking them doesn't care about distance. And now measure the spin of the New York electron. You find it is spin up. At that instant, the California electron becomes definitely spin down, not because any signal traveled between them, not because they communicated, but because your measurement in New York collapsed the shared quantum state of the pair, and that collapse happens instantaneously. Regardless of how far apart the particles are, Einstein thought this proved quantum mechanics was wrong. He said, look, either information is traveling faster than light, which violates relativity, or the electrons had definite spins all along, hidden from us, and quantum mechanics is incomplete. There must be hidden variables determining the outcome, but experiments have been done. Very careful, very clever experiments called Bell tests, and they prove Einstein was wrong. There are no hidden variables. The electrons genuinely don't have definite spins until measurement, and yet the correlation persists across any distance. Measurement here affects the system there instantaneously. This isn't useful for sending messages faster than light, by the way. You can't control what results you get when you measure. The outcome is random, so you can't encode information. But the correlation is real. Measure one, and you've instantaneously affected the state of the other. Not by sending anything between them, but by collapsing the shared quantum state they both inhabit. The implications of this are staggering. It means quantum systems aren't local. They don't have independent realities that just happen to be nearby or far apart. Entangled systems are fundamentally connected, part of a single quantum state, no matter how far apart in space they are. And measurement of one part affects the whole. You know what really gets me about all this? It is not just that measurement changes things. It is how precise and predictable these changes are. Quantum mechanics gives you exact probabilities for every possible outcome of every possible measurement. It tells you precisely how the act of measuring one property affects your knowledge of other properties. It describes the collapse of superposition in mathematical detail. The theory is incredibly precise, incredibly successful. We use it to design computer chips and lasers and MRI machines. It works perfectly. And yet, we still don't fully understand what measurement really is. We can describe what happens when you measure. We can predict the outcomes. But what constitutes a measurement? Where is the line between a quantum system in superposition and a classical measurement device that has a definite result? This is called the measurement problem, and it is one of the deepest questions in all of physics. Some people say measurement happens when the quantum system interacts with something large, something with many particles that can't maintain quantum coherence. Decoherence, it is called. The superposition doesn't collapse in a fundamental sense. It just gets spread out over so many particles that it becomes impossible to observe. Effectively classical, others say. Consciousness is involved. That measurement requires an observer, a mind that experiences a definite outcome. I've never liked that interpretation. It seems to give humans a special role in physics that we don't deserve. The universe was doing quantum mechanics long before humans evolved to observe it. Still others say the universe splits. Every time a measurement could have multiple outcomes, reality branches. All outcomes happen, each in its own separate universe. You only experience one branch, one outcome, so it looks like collapse. But really, there are now multiple versions of you, each seeing a different result. The many worlds interpretation, it is mathematically elegant. No collapse needed, but it requires accepting that there are countless parallel realities constantly being created. That is a high price to pay. I don't know which interpretation is right. Nobody does. Maybe none of them are. Maybe we're still missing something fundamental about what quantum mechanics is telling us about reality. But here is what we do know. We know that measurement changes quantum systems in predictable, unavoidable ways. We know that properties don't exist independently of measurement. We know that entanglement creates correlations that persist across space. And we know that all of this has been tested experimentally over and over, and quantum mechanics always turns out to be right. The world at its smallest scales doesn't work the way the world appears to work at human scales. Objects don't have definite positions until you look. Particles don't travel on definite paths until you measure them. Properties emerge through interaction, not observation of pre-existing facts. Reality is participatory. Your measurements matter, not because you are special, but because measurement is a physical process that interacts with quantum states in fundamental ways. And the thing is, this isn't hidden away in some abstract realm we never encounter. Quantum effects are happening all around you all the time. The reason matter is stable, the reason atoms don't collapse, that is quantum mechanics. The reason the sun shines through fusion, that is quantum tunneling. The reason your computer works, that is quantum behavior of electrons in semiconductors. This strange measurement, dependent reality, is the foundation of everything we see. We just don't notice it because large objects, objects made of trillions upon trillions of atoms, behave classically. The quantum weirdness averages out, superpositions decohere. Measurements happen constantly through interactions with the environment. By the time something is big enough to see with your eyes, it has already been measured by countless air molecules, photons, and vibrations. It has a definite position, definite properties, because the environment has already collapsed any quantum uncertainty, but down at the level of individual particles in carefully isolated systems. In precision experiments, the quantum rules apply, and those rules say measurement matters. Observation isn't passive. Looking changes what you are looking at, not because you are clumsy, because that is how the universe works. You know, Niels Bohr, one of the founders of quantum mechanics, used to say that if you are not shocked by quantum mechanics, you haven't understood it. And I think he is right. This should be shocking. Reality shouldn't work this way. It seems impossible, and yet it does. Every experiment confirms it. The math works. The predictions come true. And we're left trying to make sense of a universe that refuses to be sensible. But that is what makes physics beautiful. That is what makes it worth doing. We started with simple questions. What happens when you measure something? Can you know both where something is and how fast it is moving? What connects two particles that are far apart? And the answers we found, the answers nature gave us, were stranger and more wonderful than anything we could have imagined. Measurement changes reality. Not because we're special. Not because consciousness creates the world. But because at the quantum level, reality is interactive, participatory, and fundamentally uncertain until interactions force definite outcomes. That is not a flaw in our knowledge. That is not a gap waiting to be filled. That is the nature of the universe. And once you really understand that, once you really accept what quantum mechanics is telling us, you can never look at the world the same way again. Every observation, every measurement, every interaction is participating in creating the reality we experience. And that is not mysticism. That is physics.